Welcome to Module 3. I'm Frank Ridgich. Today we'll talk a little bit about variables, types, and I/O. So by the end of this module, you should be able to use clear variable names to store intermediate results in Python. You'll be able to distinguish basic Python types. Int, float, stir, and bool. We'll define what those are soon enough. We'll define why they matter. We'll load a small CSV file into pandas, the library pandas, and inspect types and units. We'll compute simple summaries, for example, the mean, and interpret them in plain language. And we'll also be able to explain how a simple decision rule, in this case in the form of a threshold, will connect to a metric and its costs. So let's start with some motivation and a conceptual scaffold. So imagine the fictional scenario in which there's a member of a fitness club called Dalflex, and they have a step counter. They have some wearable device like a smartwatch that's counting their steps. So the data set consists of 10 days of activity, and in every day we measure the number of steps this member took, the number of minutes they were sitting, and the number of minutes they were asleep. And what we want is to answer the question, is this person typically reaching an 8,000 step goal? So if they are on track to meeting this goal, we want to send them a little message maybe on their smart device with a congratulations and the message like keep it up. If they're not on track, so if they're not regularly meeting this goal, we want to send a reminder to maybe adjust the plan because their goal isn't being met. There are some costs associated with these two decisions. So if we call them on track, if we say you're doing great and say congratulations, but they're not, they might undertrain, they might not get enough steps in, they might also be confused. And if we tell them they're not on track, that they really need to pick it up a bit, but they actually are meeting their goals, then at the very least this is going to cause them unnecessary worry. So what we want to do in this module is to connect the variables I mentioned above to kind of types, different types of data. We'll talk about I/O, input-output, how to summarize the information, and how to make a decision. So it's helpful to think about data generating processes, or DGPs. So in this case, the DGP is a human that's just going about their day. It's also a wearable device that they're wearing that measures their steps, their sleep, their sitting time. And to some extent, it's also the mechanism that syncs to a server, which exports a CSV, a comma-separated values file type. We have a variety of variables. We have the date, which is a calendar date or day. We have a day type, so we care if it's a weekend or weekday. This is categorical. We'll define this in a moment. We have a number of steps, which is like an integer. We have minutes sitting, which is also an integer. And we have minutes sleep, which is also an integer. We already have some science-ish questions we can ask. So for example, well, how precise is the step counter? So these numbers down here, how much can we guarantee that those are actually measuring things correctly? If the user does not wear their watch one day, so there's an element, a data point in the CSV that's missing, is that meaningful? Or do we actually get days where it's like there's no information for this day? Similarly, are labels like weekday and weekend correct? I mean, obviously Saturday and Sunday are usually called weekends, but what if this person works on the weekend and they're a student and maybe they have a day off in their schedule, so they stay home that day. So the difference between weekday and weekend really matters. It really depends on context. So we basically have this chain. A person's moving. The wearable sensor is counting some data associated with their movement. There's an app backend which accumulates raw log files. This is converted into a CSV file. Call it steps_data for an example. And then this basically represents a tiny table in pandas, which is a library for handling data of this type. By the time we get it, by the time data scientists like you and I get this data, it's already been kind of gone through this process. We don't have physical access to the person or their device. Like all of the data is more or less in this tabular form. So we don't actually have access to the messy world itself. So the variables and types we have, like how we actually represent the messy world, and encode pieces of that world really, really matters. So in this course, usually when we talk about variables, this is in the mathematical sense. This is a named quantity that can take different values. The values can change over time. The values can change over different users. And normally there's some kind of a unit associated with it that is kind of implicit. So the mathematical form of a variable, the variable name would be x, and the variable value would be 67. Okay, but there's no indication here of units, for example. Often we'd prefer them to be there, but sometimes it's implicit. A Python variable is a name, some kind of textual name that's bound to a value that's stored in memory. So in this case, steps underscore today would be the name of a variable, and its value would be 8,450. You can kind of see already how these two definitions of variable are very close to each other, right? We have a name on the left-hand side, an equals sign, and then some value on the right-hand side. So like already we're seeing the connection between mathematics and coding. Now, types are a way of defining rules for what values are allowed and what operations can make sense on these variables. So for example, we can add two integers together. We can add 67 with 3, for example. But in theory, we're not supposed to be able to add a string and an integer together. Like, what does it actually mean to add some text and a number together? Now, technically, you can do this in code, we'll see some examples of this later. But in theory, this is something that we at least need special cases to handle. And finally, I/O, I think as you already know, it means input-output. This is basically how programs receive data. This can be in the form of files. This can be in the form of like APIs, like application programming interfaces that connect over the web to some other bits of code. It could even be from the keyboard or from other sensors. And then that's the input, and the output is how it sends the results of its processing out. So this could be also in the form of files, or it can be in the form of plots and figures or other elements to the screen and so on. So when we're talking about data, we first have to kind of like split it up into different categories. And coincidentally, the first category of data is categorical category. Here we have broadly the idea that data can be either qualitative, in which we're thinking about the qualities of the data, in which case we're talking about categories, this thing or that thing or the other thing, versus quantitative, which is numeric. If you're having trouble remembering these names, just remember that, well, quantitative sounds like quantity. Quantity is numbers, therefore quantitative is numeric. Qualitative has the same root as quality. Quality basically defines sort of the manner of something, how it categorizes or the type of something. So let's go through each of these in turn. First, qualitative. Qualitative doesn't really describe amounts of anything. So an example of a qualitative data type would be the day type. Either the day type is a weekday or it's a weekend. Or maybe it's a color, and the color is red or blue or green. So in the mathematical point of view, this would be something like a set of labels. So here we have like the mathematical representation. It's a set indicated by these squiggly lines of two elements separated by this comma, weekday and weekend. On qualitative data, you can do a couple of different kinds of operations. You can do equality. Is red equal to red? Yes. Is red equal to blue? No. You can do like not equality. So is red not equal to blue? Yes, and so on. And you can also use these to count frequencies. So you can count how many instances of weekday we have in a data set, and you can count how many instances of weekend we have in a data set. That's different than actually using weekday as the count itself, right? So it's a count of this label in a data set. That's somewhat of a different use case. On the other hand, we have quantitative. So quantitative values actually do represent counts directly or measurements directly. So this could be steps. So this is a count or steps per day, like some kind of ratio. It can be minutes of sleep. This can be a duration. The unit will be in minutes. So the math-ish view of quantitative or numeric data would be elements of a number set, integers, real numbers, and so on. And here, with quantitative data, we have the same operations as qualitative, so we can still check if two numbers are equal or not equal to each other. But we can also do kind of arithmetic operations, like we can add counts together. We can subtract counts from each other. We can take averages. We can take standard deviations. We can sort them, and so on. I'm going to note that there are caveats. So, in theory, the colors are sortable by their wavelengths. So, red has a longer wavelength and blue has a shorter wavelength in the real world. So, in theory, you could sort the colors, but for the sake of argument, just imagine that these are just labels for nominal things, named things. So if you can take an average of something, then usually we're talking about quantitative data. You can take the average of 2 step counts, but in theory you can't take the average of a weekday and a weekend. What does that even mean? Again, there are caveats. There are exceptions to this. You could potentially say that the average of red and yellow is orange, because we understand how colors are operate in the real world. But again, if these are just labels of things, then the average of the string red and the string blue doesn't really mean anything. So we're dealing with qualitative data. We can break down each of these types of data, qualitative data and quantitative data, into their own subsets as well. So qualitative data is basically things that we can just name. There's no order whatsoever. So nominal sounds like name. Those two ideas go together. So again, these examples are day types, provinces, team colors, and so on. So things you can do with nominal data types are, well, you can again do equality comparisons. You can count them. You can do like the proportion of times that they occur in a data set. If there are 100 references to provinces and 50 of them are to Nova Scotia, then we have a proportion of the label occurring in a data set. But the label itself doesn't represent a count of anything. You should not be able to do like inequality comparisons of the mathematical type. So occasionally in real-world data sets, there might be this kind of data dictionary in which instead of having like a label for each of the provinces, we might have a number for each province. Maybe Nova Scotia is represented as the number 1, New Brunswick as the number 2, and so on, right? But even though numbers are, you can take comparisons of them. So the number 3 is bigger than the number 1. This doesn't mean that the thing that these numbers represent, in other words, the provinces, are comparable in this way, right? So there's no, if you're going to say that Quebec is greater than Nova Scotia, then that's really going to be about something like its size or its population or something like that, right? The labels are not comparable in this way. So still thinking about qualitative data, still thinking more or less in terms of labels, there is another type of qualitative data called ordinal. So ordinal, like the name suggests, consists of data types that can be ordered. Okay, they can be ranked, but the differences between labels are not numeric, and there's no like measure of distance between them, really. So examples of these are the so-called Likert scale. So we have like extremely sad to neutral to happy to extremely happy, and there's sort of an order of goodness along this spectrum. But there's no measure of actual numeric distance between very sad, or between sad and neutral, for example. There's just an order. Occasionally when you go to see the doctor, in some situations you might be asked to rate your pain on a scale of 1 to 10. And more or less this is still doing the Likert-like scale. Like the difference between an 8 and a 9 on this pain scale doesn't really compare to the difference between a 4 and a 5, even though they're 1 digit apart. Okay? This is one of the things we have to look out for, because sometimes we have ordinal data that's represented as if it's a number, a countable number, and that's just a convenience. It doesn't really represent the reality of the data type. Again, similarly, you can have strings. Low is less than mid, which is less than high, but the differences between these things are not measured. So we can actually do comparisons now with ordinal data in a way that we couldn't do with nominal data. We can take medians and we can take percentiles of these as well, but we can't average them, right? So the average of agree and disagree doesn't really actually make sense. There's no quantity there. Again, often when you see survey data, or you're asked to provide your opinion on a scale of 1 to 5, what do you think of this or that or the other thing? You give them a number, but that number is not a number. It's a label that represents something that's in an order, but it's not countable exactly. So I want you to take a moment just to make sure this is sinking in. In your notebook, consider like the grade you're going to get in this class. It's going to be something between an A and an F. And just consider, is this nominal or is this ordinal? And why did you choose what you chose? So you can pause the video, do that exercise, and come back. On the other side, we have quantitative, right? So quantitative data consists of discrete values, values that are like separate chunks that you can basically jump from one to the next. And these are often counts, like whole numbers. So for example, the steps per day, right? So you have 0 steps per day or 1 step or 2 steps. It doesn't really make sense to have 1.5 steps per day. How would you count that? The number of logins per day is another kind of like integer or whole number. You've either logged in once or twice or 3 times and so on. Again, there are exceptions to this. Like what if somebody was beginning the login process, but they stopped before they completed the 2-factor authentication or something like that? Maybe you can say that they only, performed 1/2 of a login, but that's kind of a bit pedantic. Normally, we don't count things in that way. So from the mathematical point of view, this is really like the set of integers, fancy Z, or it can be the non-negative integers, fancy N, right? So 0, 1, 2, and so on. And then finally, continuous, another type of quantitative data. So these are values that can, in principle, take on any real value in an interval. So between any 2 values, no matter how specific you are and how close those values are together, another value is still going to be possible with extra specificity. Examples of continuous data include weight in kilograms, like 72.3 kilograms, temperature in Celsius, the heart rate as a real valued measurement, and so on. So mathematically, this is like the real numbers, fancy R. This could also be the complex numbers if you care to work in the complex plane, but that's another story. So in real data, just a bit of warning here. There's always, again, caveats, exceptions. Sometimes measurements are rounded, but we still model them as continuous. So a heart rate monitor, for example, might like round down or round up to the nearest whole value. Or you might get the temperature in your weather app in terms of like degrees Celsius, instead of like it's going to be 23.5 degrees Celsius today, right? So things are rounded, but you can still take averages. You still treat them as if they're a continuous real valued number. There are other kinds of measurement scales we're going to see in this class, including binary data. You know what this is. There's only 2 values, 0 or 1, representing false and true respectively. We can do kind of binary operations on them. So a binary operation, say, is active, asks a question about steps being greater than or equal to 8,000. So steps is a discrete integer. 8,000 is a discrete integer. You can do this comparison between them, and if it's true, you return true, and if it's false, you return false. Date time will come up quite a bit, so we're going to talk about calendars and clocks. This is stored in Python in a special data type called date time, and we'll see an example of that soon enough. This is going to be important in various ways as we go through the course. So these distinctions, the types we decide upon, really plays a big role in the summaries, the plots, and the models that we choose to apply to the problem. Here's just a little cheat sheet for everything we talked about before. I encourage you to look at it in your own time on the slides we've posted. So generally, just to return to this idea, the mathematical set, the mathematical description, generally can tell you what operations are going to be valid, because operations are mathematical, so averages, additions, and so on. We get the validity of that from the mathematics, and then the Python categories basically tell us, or tell the computer, how to interpret those kinds of rules. So here's a little example of how things can go wrong, right? So in this little bit of code here, we have 2 variables, steps and goal. And in this case, these are both strings. So in Python, this little sequence over here is surrounded by these quotes, which means that what we have is a string. So it's not exactly the number 9,000. It's the string, which has 4 characters, 9, 0, 0, and 0. Similar for this string, which looks like 8,000. So when you do an addition of these two numbers, you'd get something like 17,000, like if these were both numbers. But because they're strings, when we do the addition operator on these two variables, steps and goal, over here, this operator now is going to see that it's dealing with strings, and it'll interpret them as strings, and then therefore, instead of adding them together in a way that won't really make sense, like it's kind of hard to interpret what adding two strings together really means. So we will just concatenate. Plus on strings is a concatenation. And down here you can see this is the result of it. Steps plus goal is, it looks like 90,008,000, right? Which is like numerically not what we'd expect from this addition if these were numbers. And then we can do a comparison. So one thing I want to mention here, which I encourage you to look up yourself, is this try statement. So occasionally things can break, and we want to avoid that. So if we want to compare steps being greater than goal, Python will let you do this. But this inequality operator will not compare these numbers in terms of, or these strings in terms of the numbers they represent. They will compare them in terms of their order that they would appear lexicographically, or in other words, in a dictionary. So if these strings were in a dictionary, 8,000 would occur before 9,000. So in some sense, the word 8,000 is less than or before the word 9,000. So when we do this comparison, we get true. Now, this is risky, right? So trying to do an operation like this on things like an inequality, which normally we'd expect numbers, on two variables which are actually strings, we could break things, and we may not be sure if they break things or not, which is why we kind of put this line, this print line, which has this kind of spooky-looking comparison, in this exception handling try statement. What this is saying is we'll try everything that happens under me, like indented under me, and if anything breaks, like if there's a type error, if I'm using the wrong kind of type for an operation, then catch it, and then you jump down here to line 10 with this exception. So if Python said, this doesn't make any sense, there's an exception, it'll jump down here. If it's a type error, if I'm trying to do something and the types don't make any sense, it'll catch the type error, it'll call it E, and then this statement down here just prints it out. In this case, we don't actually catch anything because this comparison is valid, but I just wanted to flag it for now because this will come back again later. So let's talk a bit more about Python variables and types. So in Python, there's various basic types that we'll lean on quite a bit. There's integers, which represent our whole numbers, float, which represents our real valued numbers, str, which represents our strings, our text. So strings like weekday, bool means boolean, this is true or false. And in pandas, the library we're going to be exploring, and use numerical columns, so a column of data in like a spreadsheet basically, often are transformed into either int64, that's an integer of precision 64 bits, or float 64, which is a floating point number with precision 64. So that's all good. If there's data in your table that looks like categories, so if it's something like a string like weekday, this will be either represented as objects or possibly as category. There's a special type called category, which basically represents our nominal data. So here is some example for you. You can copy this into your Python environment. We have an integer, we have a floating point, as you can see from this period. We have another string indicated by these double quotes. We have a Boolean, so hit goal over here is our variable. It wants to get a value. What value does it get? It gets the value from everything on this right-hand side of the equation. What's on the right-hand side of the equation? Well, it's a comparison between the variable steps today and this integer 8,000. Steps today is 8450. That is greater than or equal to 8,000. So this will resolve to true, and then the Boolean value true will be stored in hit goal. Regardless of the values, we can still check the types of all of these variables. So we have, what is the type of steps today? What is the type of average daily steps, and so on. And as you can see from the result, that the slides automatically generated, The types are int, float, string, and bool, as we expect. So all good so far. Let's go into the math a little bit. Let's talk about mean values, because we'll be dealing with floating point values soon enough. So consider that we have step counts for every day in our data set, and we want to average them. So we basically want to count the total number of steps and divide by the total number of days. As you know, the way that we compute a average is shown here mathematically. So this is the sum from the ith day, where the first day is 1, all the way to the nth day, where n is the total number of days we have in our data set. X sub I, that means x subscript I, represents the number of steps we've measured on day I. So day 1, then day 2, then day 3. We add all of them together, and then we multiply by 1 over n, which, as you know, is the same thing as dividing by n. And the overall result is what we call x bar. We call it x bar because there's a bar on top of x. And this is the measured mean of the values. So in code, so that's the math of it. In code, we have something like this. This is our data. We have n equals 3, which we can get automatically by calling len on the steps list variable, which we previously specified as this list. It's a list because we have square brackets surrounding elements separated by commas. So the n is going to be 3 internally. There's a internal function called sum, which knows to take a list of numbers to just sum up all the numbers. So basically do what's happening here. And then we just divide by n, which we've previously computed. And then this is kind of printing it out. We just specify, write it out, and then Python writes it out for us. You can take a moment now and just make sure that the average of these 3 numbers is actually 7866.666 repeating, if you care to. There we go. So let's talk about variables, names, and objects for a moment. So in Python, a variable is a name that's bound to an object. And we can sometimes think of it as like a little box. A variable's a box, and there's a value inside of the box, and there's a label on the side of the box with whatever name we've provided. That's one way to think about it, but it's going to be a bit more tricky than this, because really what's happening is there's unnamed variables in memory, and we have labels that point to that same point in memory. And that's a little bit of a different thing, right? Because we can have 2 labels pointing to the same object. And if we change the value pointed to by one label, it'll simultaneously change the value pointed to by the other label, because they're both pointing to the same area in memory. Here's a little example. We have pardon me. There we go. We have a variable, steps A, which is, again, a list of numbers. We have steps B, and we say steps B is equal to steps A. This doesn't make a copy of this list and then point another name, another label to that copy. This is, all it means is there's a list somewhere in memory, and both steps underscore A and steps underscore B point to that same area in memory. There's another built-in function in Python where we can take a list variable, like steps underscore B. We can call a function on it, so dot append says run the function append on this list, and actually do it in memory, and append, or add to the end of the list, the number 9100. Okay. Now you can run this yourself, and you can print steps A, which previously was defined this way, and then you can print steps B, which was defined as being steps A, and then having 9100 added to it, and see what you get. So I'm not going to include the output here, but I want you to actually run this and see what you get. Hopefully, you'll see that both steps A and steps B now point to the same value, because these are 2 names that are pointing to the same list object. And when you change that list object, the 2 labels are still pointing to that same object, so when you call one, it'll call the other. And you can make this explicit, so you can say ID. ID basically tells you the memory identity of a variable, like where this variable is stored in memory, and running this in your Jupyter notebook should provide two identities which are exactly the same. So remember, names point to objects, and assignment usually changes which object a name points to, but not the object itself. But there are some kind of slight exceptions to this, which you'll really have to become familiar with through practice. So some objects can be changed in place, which means that they're immutable, and others cannot be changed in place, which means they're immutable. Let's look at immutable first. So look at just a single number. So x equals 3, and then y equals x, and then y equals y plus 1. When we run line 4, what we're doing is taking the value of y, adding 1 to it, and then storing it in the place where y is. This will actually create a new integer object, and then when we print x and y, we should be getting two different numbers, 3 and 4. This is different than the mutable list, which we just saw a moment ago. This is basically the same example. We have a list of 3 numbers. We call that list one thing. We have another name for that same list. In line 10, we append a new element to the list pointed to by the second of those names. And then when we print the lists pointed to by these two names, we'll get the same object. So immutable types are integers, floats, strings, tuples, these basic types. And mutable types are lists, like we've seen a moment ago, as well as things called dictionaries, which we'll see later in the course, and many kinds of pandas objects. Why does this matter? When you have a function that modifies a list or a data frame, which is like a data type in pandas, we may change the data for other variables that point to that same list or data frame. And if you're using a Jupyter notebook where you can change cells in different orders, this can be a problem because you might forget where this mutation occurred, right? So generally, especially when we're using pandas, it's going to be very careful to pay attention to which operations copy data into a whole new object versus actually change an object in place. Okay, and if you want 2 copies of the same object, you should be explicit in making copies. So in Python, in a script, like a good old-fashioned Python script, a .py file that you run, in a standard sort of environment, that Python script will run from top to bottom essentially once, right? But in a notebook, you can run all of our cells in different orders, as we've seen. So I would like you to open up a Jupyter notebook, create 3 cells, 3 coding cells, put line 2 here in one of them, value equals 10, copy line 5, value equals value plus 5 in the second cell, and then write print value in the third cell. But don't run anything yet. If you run cell 3 first, before you do anything else, so far we don't have a variable called value defined yet, so you should be getting something like a name error because the name value has not been defined yet. And then I want you to go back up, run cell 1, and then run cell 2, and then run cell 3, see what happens. And then now rerun cell 1 after you run cell 2, and then go to cell 3 and run cell 3, right? So go 1, 2, 3, 1, 3, and see what happens. When I run cell 1 again, whatever is stored in value will go back to 10, and when I print it out, you should see 10, even though I've, in theory, added the value 5 to value after or below cell 1. That doesn't really matter because I ran cell 1 after I ran cell 2. So I want you to try this out, really. So this is simple, but it's important for you to kind of get the gist of it. When you're finally done, I want you to use run all to make sure the notebook works from top to bottom. As we'll say later, like avoid using generic names like data or df for your variables. Make sure the names are as descriptive as possible, but just for the sake of example, we'll keep it simple here because we're just giving examples in slides. It's helpful to keep related code together, so code that performs a simple function, keep together and don't have things spread out all over the notebook. Be hygienic in terms of like how much code you have and where it's located, and be generally aware, if you can, about the hidden state, right? So the hidden state, the actual values of all of our variables, and how they can change is a big source of these problems of saying it works on my laptop when I just restart Jupyter, but it may not work on someone else's laptop if the hidden state is not accounted for. Sometimes we're going to want to transform data from one type to another. In other words, we want to cast the data from one type to another. So in this example, we want to be able to convert between strings and numbers. Like earlier we saw a string that looked like a number, but it was actually a string, and that might have caused some confusion. So here we want to be a bit more explicit about handling this type of situation. So in line 1, we have the variable steps underscore string, or str, string. And again, it's I put in a string with 4 characters, 8450. Now this string represents in some way an integer, right? Like there's no decimals, there's no other kinds of characters. This looks very much like an integer, but technically it's a string. So if I want to just extract the integer and transform this string into the integer it represents, I just use a simple built-in function, int. Int can take in a couple of things, a couple of different arguments, one of which is a string. And if that string looks like an integer, then int of that string returns an integer, and now I can store that integer in steps underscore string. I can also convert it to a float, so even though there's no decimal point and a 0 or any other numbers after the decimal point here, which normally is a dead giveaway that it's a real number or a float. I mean, technically 8450 can be represented as a real number, 8450.0. So the built-in function float performs basically the same task. Float, taking in a string, extracts a floating point representation for that string, and then in this case I return it into steps underscore float. So I can do a few things now, like when you run this yourself, and again, just copy this code, run it on your own platform. When I add the digit 1 to steps int, you should see the number 8451. Steps underscore float divided by 2. You can try to guess what's printed, and maybe even write that down first. Run it, and then see what happens. We can also convert like integers, floats, back into strings. So str is a built-in function that in this case is taking an integer, the steps int. And in this case, I'm just converting it back into a string, so strnum. So here, print you walked plus string num plus steps. Here, I remember when I'm doing the addition operator, but on either side of it are 2 strings, what this means is concatenate them together, like join them one after the other. Which is kind of why I have this space here, because string num doesn't include any spaces in it. So if I want this word representing this number to be printed with spaces around it, you have to kind of take care of that here, as you already know. So there's useful built-ins, int, float, string. We've seen examples of how to use that a moment ago. There's also Boolean. Boolean, I suggest just playing around with it for a little while, because it might not necessarily behave in an intuitive manner. But essentially, like for example, for strings, if a string is non-empty, like 42 is not an empty string, that would be considered to be true in some sense. But if the string is empty, like if it's a string with no characters at all, then this would be considered false. This is more of a practical reason for that. So generally, we want to be as explicit as possible about any kind of conversions at any boundaries. So if you're taking in data, or if you're writing data, or if you're asking the user for input, or if you're parsing information in a CSV file, try to be explicit about what the types are by casting them in this way as appropriate. Sometimes this can fail, right? So let's look at some possible error messages. Because not all strings are going to be valid numbers that can be passed into those pre-built functions. Consider for a moment bad underscore steps being the string NA. This basically means not a number. It's something else that's not a number. It's an inappropriate data from the point of view of its type. Again, we have this try except kind of block where we try to do something, and if Python doesn't like it for whatever reason, it will throw a flag. It'll raise an exception. That exception will be caught, and then we can do some handling of it. So you should try to run this code. So again, bad steps is the string NA. We previously saw that we can pass strings that represent numbers into the function int and get the integer out of it. But what integer is NA? So if you try this, you might get an error. There's various kinds of errors you might get. So a type error refers to you're just using the wrong kind of object. So in theory, if you take the string 8,000 and subtract the integer 1 from it, like what does that actually mean? This is a use of the minus sign with two different kinds of types that don't really play well together. A value error is, well, the type is okay, but the value doesn't make any sense. So we already know that we can pass a string to int, but the value NA is not an integer, so you might have a value error at this point. Anyways, again, as always, copy this code and run it yourself. Reading error messages of this type is a very useful skill. So generally, you might have an exception type, and if it's a value error, you know what that means. If it's a type error, you know what that means, and so on. Usually when you get an error message, there's all of this other text that comes up indicating near the bottom like what line this occurs on. In this case, you might get an error saying there's a problem at line 4, or whatever the line number is when you copy and paste this. And when you have that, then you can go back and check your code and try to debug the problem. So speaking of not a number, so NaN, or not a number, is a placeholder that we see in Python, and it actually serves a good purpose, sometimes through calculations or through reading a table with missing values. Python or its libraries will automatically convert problematic data into just not a number. It's not a number, I don't know what to do with it. What you end up getting is something that looks a lot like this. So here's another list. It's a list of 4 elements. 3 of them are valid integers, but this one in the second position here is a not a number token. And we get it from NumPy. So NumPy is called NP. NP has a special token called not a number. But we can still incorporate not a number into a list of integers. And when we call the pandas function series, which like for now, just consider it as sort of, it's a way of representing an ordered list. It does so without any problem, and it stores it in variable s. And you can print it. And let's see what happens when you print it. You can also print sort of some statistics on it. So you can print what is the mean of these 4 elements. You can print what is the count of these 4 elements. And this is subtly different than what is the length of these 4 elements, for reasons I'm going to get to in a moment. So here's some key behaviors. First of all, sometimes it's useful to know that not a number is contagious in a sense. It'll propagate. So for example, you can add a not a number to x. This is not going to raise a type error, at least it shouldn't. But the result is going to be that this is also not a number. It's like adding any number to infinity and you get infinity. Same kind of concept applies here. If you apply something that's not a number and you add it to a number, then whatever you get is also not a number. And this is where the contagion happens, and the not a numbers can kind of spread through your code. Usually aggregations or statistics like mean values will just skip not a numbers by default. So when you run this code yourself, you should see that the mean value you get in the print line on line 6 will be the mean value of 7,800, 8,200, and 7,600. Len s will count all the elements. So it should return to you the number 4 because there are technically 4 elements in it. But scount is kind of smart enough, I guess, to some extent, to know that, well, I probably don't care about the not a numbers. I only care about the things that actually are numbers. So scount over here should return the number 3. But try it out yourself and see what happens. So we're going to do a proper treatment of what it means to have missing data in a future module. I believe it's going to be module 13, but we'll get back to that in a moment. But for now, I just want to flag that not a number is a special token that comes up a lot in data science, and we'll just recognize it for now. Here's a little thing to note down and to consider. When you have a missing value, say a missing step count in your data that we've been dealing with this fictional example, is this missing data, is it kind of more similar to 0 steps, or is it unknown, right? So if somebody, didn't put on their wearable device and they didn't walk at all, then they didn't walk 0 steps, and we wouldn't have recorded any information, so therefore it's not a number. But is it really, right? Is it more unknown? Maybe they did a ton of walking that day, they just didn't have their smartwatch on them, so not a number could also be unknown. So I want you to think a little bit about this. And under what circumstances is not a number sort of the same thing as 0 or nothing? And in what circumstances would not a number mean, like I just have no idea what it could possibly mean? And there are some situations where it could be one or the other. So think about it intuitively, pause the video as necessary, and come back to it when you have written down your thought process. So a few more things. So again, we're going back to our DAL Flex Club data. Here is a small CSV, I guess, a spreadsheet. We have 3 data points, and we have a line at the top, which is like the titles of our variables. So these, like having 3 quotes over here, allow us to have a string that kind of, has this shape to it. So date, is the first column, date type is the second column, and steps is the third column. So we put all this string into this variable called CSV text. Now we have this function, which I import from the IO library, which I call down here, which imagines that I'm reading a file from a CSV file, like a file that has this content in it. And it kind of transforms the data in a very slight way so that it looks totally unambiguously like CSV. It might raise some errors if there is like some problems with my text here, my string. And then it'll pass that representation into a pandas function called readCSV, which does as you'd expect. It reads all of this data in a CSV format, and it produces what we call a data frame, df. And df has a built-in function called dtypes, which will tell us like what are the types of all of our variables that I'm storing in my data frame. So it might be the case that we want to represent the dates as a special type called date time. We saw earlier that sometimes we have this special type that is not a string, it's not an integer, it's something else. And dates are kind of weird in some sense, right? Because sometimes when you add 5 days to the last day of a month, you get the 4th day of the next month. Sometimes you get the 5th day of next month, depending on what month it is, and so on. Sometimes if you add a certain integer to minutes, that rolls over to a number of hours in a way that adding an integer to hours does not roll over in the same way to days, and so on. Anyway, so like dates are special. We need a special format for them. Fortunately, there are ways to convert strings that are written in a standard format. So here we have like 4 digits, or 4 characters for the year, dash 2 characters for the month, dash 2 characters for the date. And the function toDateTime within pandas can take a string and then convert it to the special datetime special type. So here what's going on is I'm taking my data frame with square brackets and a string inside of it, basically takes the column of the data and then returns that column as sort of a list or a vector, which is in this sense the same thing. So it takes this first column of data. And then for every string in it, it'll convert it to datetime, and then it'll produce a list of datetime objects, one for each of these 3 strings, and then we'll store that into the column for df date. So I'm kind of replacing all of these strings with date type objects. We can also convert these weekdays. So these are still strings for now, or they might be stored as objects by pandas. But I can say specifically, these are not just any kind of old objects, which can include strings, but specifically they're categories, which means they're nominal data, which we talked about earlier. So we can take all of the whole column of the column with the label date type, and for each of them, say, calling as type will convert it to a category. So a category is the type of data I want to reframe this as or cast this data as, and then I'll store that recast data type category in that column. And then when you run df dtypes now, as you did earlier, you're going to get a different set of types. So object, like I mentioned a moment ago, is Pandas's generic type for strings and mixed things and kind of a generic data. Category is a type of object, but it can be used specifically to save memory or encode meaningful sets of labels. This can matter if you're dealing with very massive data sets. And like I mentioned earlier, also datetime can support arithmetic, and spans, compute the number of days between 2 events. It can do sorting and filtering in a way that is date specific and wouldn't necessarily apply to any old text. So we're going to see this more in Module 7 and 8 when we talk about series and data frames and loading data. Again, I just wanted to flag it for now.